Hello, I'm calling this video The Oxidative Stress, Who We Are and Why We're This Way. I'm in it to describe a new approach to understanding and treating the symptoms of long COVID, chronic fatigue, and chronic illness in general. My name is Lisa Marie Korst. I'm a former physician, and I'm now a medical researcher. Most of all, I'm a patient who's collaborated with others and found some solutions. And it's my hope that we can move forward awareness so that we as patients can recognize oxidative stress in ourselves, how it feels, and that doctors can test for it, treat it, and help people heal. Now, I have a few disclaimers. I'm not a nutritionist or biochemist, and I'm not giving medical advice. I retired my MD license long ago. However, it's really important to me that I share this information. It's helped many of us manage our symptoms, and there's so many people that are suffering with these symptoms today. So use your discretion and work with your doctors, please. So I want to explain the concept of oxidative stress and how it explains the symptoms of long COVID, chronic fatigue, and many other chronic conditions. Now, I'm not referring to the acute symptoms caused by COVID, but the long COVID symptoms, such as those described in the NIH RECOVER trial. And they found the top 12 symptoms for long COVID, and they pretty much sum up the situation. We have fatigue, or post-exertional malaise, which is fatigue after exercise, brain fog, unexplained inflammatory symptoms and pain, and this can happen anywhere in the bowel, bladder, brain, eyes, skin, joints, depression and other mood disorders, dysautonomia, what's referred to sometimes as POTS, unexplained tachycardia, where your heart rate is just going too fast, migraines, tight throat or chest, shortness of breath, cold hands and feet. These are all symptoms that are prominent in people who have long COVID and chronic fatigue. And we want to try to describe where they come from. And where I'm positing is that oxidative stress is responsible. We all go to doctors to fix different organs in our bodies, but we generally don't go to doctors to fix our biochemistry. Yet we're understanding now that chronic disease is a biochemistry problem. Diabetes, hypertension, cancer, Alzheimer's, Parkinson's, they're all caused by dysfunctional biochemistry that leads to inflammation. This dysfunctional biochemistry is called oxidative stress or overload. And what it is are chemical reactions that are known, that produce what are known as free radicals, or these unstable molecules, sometimes referred to as oxidants, that can steal electrons from other molecules and cause a chain reaction. And these free radicals directly trigger immune cells. The cells they trigger are referred to as mast cells, M-A-S-T. And these can spill inflammatory compounds. Most, if not all, chronic disease is now believed to be a result of chronic inflammation triggered by oxidative stress. So here we have stress at the cellular level, not the organ level, but the cellular level. And these are where we find chronic oxidative stress symptoms. This is where we have the chain reactions from the free radicals that trigger the mast cells that go on to trigger chronic inflammation and mitochondrial dysfunction, and from there go on to trigger chronic disease. Now, these diseases down here, they all have names. You know, this is where we get the Alzheimer's or the or depression or you know, a lot of the inflammatory diseases that we were talking about as being chronic, diabetes, etc. These up here are really pretty vague symptoms, as described in that trial. They often don't have names, and we need to learn how to recognize these, and because these are the hallmarks of oxidative stress. So we're looking at oxidative stress. It's an imbalance or an overload, too many free radicals for the body to handle. So we have these healthy atoms or molecules, and then free radicals come along and they steal electrons So they're stealing the electrons and will, then cause the healthy atom to become unstable and then create a chain reaction. Antioxidants come in and they can donate electrons without becoming unstable. So they can stop these chain reactions. That's what an antioxidant is. Now, what happens is we get into this vicious cycle. Our natural antioxidant systems get overwhelmed and free radicals bump up against the mast cells and trigger them. So we get what's called this autotoxic loop, where we have the free radicals being produced, triggering inflammation, that causing more free radicals to be produced, and this just goes on in a vicious cycle. Some of us never resolve it, and we don't reboot, and this is the state that we tend to find ourselves in. Symptoms show up in various parts of our body. And, if you don't reboot, you can go on to get chronic disease, which can come in many forms. But we really don't know why one person will get diabetes and another get cancer, for example. So let's take a step back then. If oxidative stress is the culprit, what causes oxidative stress? Well, if you go into a doctor complaining of what you have, all those symptoms, doctors often think about environmental toxins, things external to your body as causing this. Pollution, pesticides, heavy metals, mold, all these things that maybe you are exposed to that is triggering your body to make these free radicals. But we have to understand too that internal processes may contribute. In fact, internal processes may entirely be the cause. Just digesting food will cause you to produce free radicals. Hard exercise causes you to produce free radicals. We know this because we have sore muscles after hard exercise. What is sore muscles? Inflammation. Okay, so we have also lifestyle things that we're conscious of that may produce free radicals. Chronic psychological stress, smoking, alcohol, lack of sleep or exercise, all these things. But yet, so many of us feel like we have all this fairly under control, and yet we're still in this boat and still have these symptoms. Now, there is a molecule in our body that, when it's produced, can lead to unrelenting oxidative stress. And this molecule is called nitric oxide. It's an nitrogen and an oxygen. And unless you're an athlete, you probably haven't heard of it. It's a vasodilator. That's its principal property. It opens arteries and brings blood flow or oxygen, right, to the muscles. Now, you will know about it when you think about it, because people use nitroglycerin for chest pain. They put the nitroglycerin under their tongue and it's absorbed and it's turned into nitric oxide, which opens the blood vessels and brings oxygen to the heart muscles to relieve the chest pain. Okay. How does it do that? Well, it opens blood vessels by relaxing smooth muscle. Here we see the arteries, and our arteries, which have, carry our blood away from our heart, are lined with smooth muscle because this controls the tone of the muscles. Is the artery squeezed or is it open, right? Nitric oxide opens the blood vessel. Okay, not enough nitric oxide causes it to be squeezed. We just talked about that nitric oxide will relax the smooth muscle in the arteries in the heart, but it relaxes smooth muscle throughout the body. And we have smooth muscle not just in the arteries, but in the bowel, bladder, esophagus, bronchi. It distinguished it from like the muscles in your arm that are, skeletal muscle. Okay, but there's smooth muscle and there's skeletal muscle, and nitric oxide relaxes smooth muscle. So let's think about this. If we don't produce nitric oxide well, and we don't have good levels of nitric oxide, then we get smooth muscle spasm. The muscles squeeze. Okay. What happens if that with the muscle in the blood vessels? Well, we squeeze those arteries, we get hypertension, right? We squeeze other arteries in our brain, we can get migraines. We squeeze the arteries behind the eyes, we can get optical migraines where the rotors start going, in your vision. You can get the arteries in your lungs squeezing and lead to pulmonary hypertension where it feels like it's hard to breathe. And if the squeezing is really severe, then it can lead to strokes, which is, in the brain, squeezing the blood vessels in the brain, or in the heart attacks. So, all of these symptoms can be caused just by it squeezing blood vessels. But what about the other places in the body where we have smooth muscle? We have it in the back of the throat, the pharynx, and the esophagus, where you can get a tightness or difficulty swallowing. I had at one time a corkscrew esophagus where the whole esophagus was in knots. I couldn't swallow at all. You can get it in the bowel where you get cramping and diarrhea. You can get it in the bladder where you can have urgency. And you can get it in the bronchi, what we know as asthma, where the airway in the lungs will squeeze, wheezing, okay? But nitric oxide also has another property that's really important to know. And if nitric oxide production is compromised, it produces this oxidative stress. It will produce superoxides. It will produce something called peroxynitrite, which is spelled out ONOO with a little negative for the extra electron here. I refer to this as ONOO because if we're not producing nitric oxide, we're producing this ONOO. And if you produce this big free radical, it triggers mast cells from the immune system to release inflammatory compounds. So here we've got this molecule that is essential to the body. And if it is not produced properly, will cause both smooth muscle spasm and this unrelenting oxidative stress. So what is going to cause us to become deficient in nitric oxide? Well, it comes from two sources. We get nitrates in the food that we eat. Things that are really high in nitrates are beets, chard, arugula. So you can get it from there and can produce nitric oxide. It is also internally produced by endothelial nitric oxide synthase. Endothelial is a lining of the blood vessels. And then the nitric oxide synthase, this is an enzyme that makes the nitric oxide. So we have in our body, in the lining of the blood vessels, we have this enzyme. And an enzyme is like a kitchen. It brings all the right things together to make something, okay? In exact right amounts. And these are what they call the cofactors. So everything comes together in the right amounts in this enzyme. And this enzyme makes this reaction happen so that it produces nitric oxide. But this is a very tricky enzyme. It's been hard for people to understand and work with and I refer to it like as Goldilocks syndrome, because everything's got to be just right. If you don't have enough of what needs to go into it or too much, the enzyme will not make nitric oxide and instead makes the ONOO. All right. So what does this enzyme need? What does enos need? Well, the first thing the thing that often triggers it to go in this wrong direction and make the free radicals is something called methylfolate. Methylfolate is simply vitamin B9. And I'll remind you that vitamins are things that we need to eat in order for our bodies to work. So there's things we don't normally produce ourselves, but that we eat them, like the sailors they learned the sailors needed vitamin C, the lemons, to prevent scurvy, right? So remember that from when they discovered the vitamins. But methylfolate is vitamin B9 with what's called a methyl group, one carbon, 3 hydrogens attached to it. This methylation is part of what is a very prominent system in the body called 1-carbon metabolism. And by putting that methyl group on the vitamin B9, it signals the body, it's a specific code for what to do with it. For example, histamine, which is also produced by the mast cells when you have an allergy to like pollen or something, histamine needs a methyl group for your kidneys to recognize it and pee it out. So this methylation process works in thousands upon thousands of reactions in the body, and we need this vitamin B9 methylated. So COVID has been described as a methyl ether or as a methyl assault. It depletes the methylfolate in our bodies. And this is what has often been postulated to lead to this reaction of the producing the free radicals and then leading to the long COVID symptoms. Other things that are needed by this enzyme are B12, B2, B6, and these are all often depleted when we're in oxidative stress. So these can get low. Glutathione can get low. Glutathione is a natural antioxidant that is produced by our own bodies, but it becomes depleted again when we're in states of oxidative stress. And one that's really key and then people don't know about much at all is something called BH4, tetrahydrobiopterin. About a third of people can't really make this very well, but without this BH4, nitric oxide synthase doesn't work. So if you're low on any one or more of these, you're going to have a hard time keeping the nitric oxide synthase functioning and your nitric oxide levels up. And it will be harder to get out of this autotoxic loop. So here is just a diagram. We have these cofactors that we really need in order to make the nitric oxide, to allow this nitric oxide synthase to work. If we're missing them, we end up in what's called this uncoupled state. And if we have them, we can stay in this coupled state and make nitric oxide. If we don't have them, we're producing free radicals. Now, the coupling business is simply about electron transport. And I'm going to leave that kind of as a black box right now, just so it really can't explain, but it's all about how this enzyme moves electrons in order to make what it needs to make. So just understand that this is some of the language that's used around nitric oxide synthase. If it uncouples, or if it stays coupled. So what does this feel like? What does this feel like when we get this uncoupling? And it's very specific. It's very direct. We can get a sudden onset of symptoms when we run out of cofactors. Let me just describe a situation that's very typical. You started to run up a flight of stairs and all of a sudden you go, whoa, I've got to stop and sit down. And you can't find it hard to catch your breath. And this just, you're a normal, healthy person, but somehow this kind of just grabs you. So what happens is the blood, you start to exert yourself, the blood starts coursing through the arteries, you get the stimulation of the production of nitric oxide in the arteries as the blood is starting to move through there. It uses up the cofactors and you can't produce nitric oxide anymore. And you got to sit down. Okay, the very typical type of presentation. Depending on where this is happening in your body and what kind of symptoms you tend to be prone to, you will see these kinds of reactions. So so the first one I described is like the smooth muscle. So you can get the shortness of breath, which is the constriction of the pulmonary arteries and causing you to sit down and stop. You can get hypertension, throughout the body. You can get migraines. You can get esophageal spasm, irritable bowel or bladder. These are all things that are happening with the smooth muscle when the nitric oxide runs out. Other things that happen, those free radicals are directly toxic to the mitochondria. So you get fatigue, brain fog, hunger, the cell shut down. The mitochondria produce the energy of the cells. So if you can't produce energy, that cell's not worth very much. We have inflammatory response, and this inflammatory response comes from the free radicals hitting the mast cells. The mast cells release inflammatory or pro-inflammatory compounds, and we get pain. We can also get other symptoms that people don't realize are related to the mast cells, like endometriosis, which the mast cells have something called nerve growth factor, NGF, and that, when is released, can trigger inflammation in a way that produces endometriosis or adenomyosis in the uterus. also prostatitis, interstitial cystitis of the bladder, something called burning mouth syndrome, where you get inflammation in the mouth particularly as you're eating something or taking something or just had a reaction to something, a headache, macular degeneration and retinopathy. And you have to remember the eyes, because the eyes have the highest density of mitochondria in anywhere in the body. And so they are very susceptible to this whole oxidative stress process. Another aspect of this is this decreased methylation from this one carbon metabolism, because our neurotransmitters, to make dopamine and serotonin, we need to have these methyl transfers. We need methylation to do that. If we don't methylate well, we often have anxiety, sadness, depression. Okay. But one other thing also that people don't realize that needs methyl groups is moving norepinephrine to epinephrine. Norepinephrine and epinephrine control our heart rate and blood pressure, and we can often get a disconnect, and the norepinephrine backs up when we can't transfer that methyl group to make epinephrine. So we get what's referred to as a dysautonomia or postural orthostatic tachycardia syndrome. Now it's really starting to sound like long COVID, and say, I get it now. You know, this is kind of where and why all these different weird symptoms start to show up. Up to this point, you know, everything I've presented is in the literature. I'm not making any of this up. This is the current state of knowledge. The problem is that many researchers have not connected the dots between this chronic oxidative stress and the nitric oxide depletion. And so often there's little headway being made regarding what is causing this constellation of symptoms, and you know, people don't realize this connection. Nitric oxide depletion and unrelenting oxidative stress have been confirmed in chronic disease, particularly heart, lung, and diabetes. Now, you got to remember, diabetes is a disease of the lining of the blood vessels where nitric oxide is produced, where endothelial nitric oxide synthase lives, okay? Pharmaceutical companies are trying to find a way to keep this enzyme in the coupled state so that it's working all the time. It's like the holy grail in diabetes. We just haven't really heard about it. But when you think about it, and it just totally makes sense, because nitric oxide depletion explains all of these symptoms that people have. Now, I want to take this a step further and continue to connect the dots and ask, is there a role for genetics? Because this is the next step where people really need to begin to connect the dots as to who is susceptible to this oxidative stress. 20 years ago, they completed the quote unquote the mapping of the human genome. The human genome, again, is DNA, right? You have the DNA, this double helix, and you have these, you know, what they have, the code, the base pairs that are all connected along here that actually make a very specific code for the DNA. And this DNA codes for genes, okay? And the genes in the DNA can code for enzymes, you know, like nitric oxide synthase. So all of the little chemical reactions that we're having in our bodies all the time occur through these enzymes, and they're coded for by the DNA. And what, you know, they're realizing, and, you know, and they're starting to map out, is that everyone does not have the same code for the same enzyme. So how I make nitric oxide synthase, I may not be as good at making nitric oxide as you are, because my nitric oxide synthase might not work as well, okay? So in this example, my family has at least 5 variations in the normal code for nitric oxide synthase. And these variations make us produce less nitric oxide compared with the normal code. So, and especially because we've got it both from my father and from my mother. And these variations are common, and they're not, you know, zebras. You know, people say, well, Lisa, I don't have any genetic problems. You know, your problems, you know, are, you know, not related to my problems. I'm talking about common, variants, things that may be in 30% of the population. And what happens in our family is that not only do we have these variations in endothelial nitric oxide synthase, we also have it in making this other real key cofactor, BH4, in the one-carbon metabolism and methylation pathways, and in the antioxidant pathways, in glutathione, for example, to mop up the free radicals. And they're all common variants, but what we're seeing is that these are combinations of things, not a single gene that causes us problems. So we have trouble making nitric oxide and trouble making antioxidants to romp up the free radicals, then we're going to develop oxidative stress. And these combinations of these common variants kind of come together where we have problems in all these different areas. And so, all these back doors to, when something doesn't work well in the body, we often have a back door, a workaround. But when we have problems with the workarounds as well as the main pathways, we may end up in some trouble. So the question is, if we replace what our bodies are not making properly, will we feel better? And this is the very question that's being asked by this whole new science called nutrigenomics. How do we eat and supplement around the variants that we have when we can't, when we have these kinds of deficiencies? So this is what I think is happening. I think we've got these genetic variants that cause us not to be able to produce nitric oxide well. We get hit by COVID or another insult and start depleting, these cofactors, nitric oxide. We develop the oxidative stress. We end up with inflammation and mitochondrial dysfunction, and then that leads to organ level symptoms and diseases, chronic diseases with names, right? So cancer, diabetes, hypertension. Here, these things just, up here where this is happening, we don't have names. But what we need here is we need to be recognizing up there. We want to be treating as high up in this cascade as possible. We do not want to be treating down here. So we have several potential treatment avenues that this all suggests. And this is where you need to start thinking about what you can do. The first one, obviously, is the nitric oxide. Support that nitric oxide the best that you can. Once you get it coupled, you can add on the food to help you do that. Antioxidants and mitochondrial support. And we know a lot about this from the chronic fatigue experience, how to help our bodies in this way. One that a lot of people don't think about is the mast cell stabilization. So if we come down to that end where we're producing all these free radicals and we're triggering the mast cells, what can we do to keep those mast cells from spilling those compounds out? Can we stabilize them? And there are several drugs and several approaches to doing that can help with those symptoms. Methylation and this one carbon support. Many of us, at least a third of us, have problems with methylation. And so this is the other way. So we've got these 4 avenues. And through addressing these 4 avenues, we've been able to manage symptoms. You don't want to do this all at once. I'm going to put a precaution in here because sometimes I start to talk to people about this and they go home and they just start taking everything and they put themselves in bed. Okay, you do not want to just throw this stuff all back at your body. This is not how it works. Your body has taken years to make these workarounds for not having this stuff. And you need to be very cautious about how you move this forward. So people say to me, Lisa, I don't really need to understand how all this works. Just tell me what to take. And I gotta go, no, you do need to understand how this works. You need to understand that if you have smooth muscle spasm symptoms, you need that nitric oxide support. If you are having trouble from fatigue and energy and brain fog, then you need those antioxidants and mitochondrial support. If you are having pain and inflammation then you need to stabilize the mast cells. And if you are having specifically problems with anxiety or depression or the tachycardia, as I explained earlier, those are very responsive to methylation. So it's important that you get the basics. And I'll make another video that describes in more detail how to get started treating and how to use these different avenues as you recognize the symptoms. So in summary, this is an open call for people to begin to become aware of the impact that oxidative stress has on their bodies, what it can do, how it feels. Treatment can include normalization of methylation processes and nitric oxide levels. I hope that younger people begin to pay attention and maybe can avoid some of the problems that we've all developed. But there's so much more work to be done, not only to understand the science and the treatment and to educate people, but to guide the development of protocols so that we can begin to diagnose and treat oxidative stress that is based on experience. Thank you.